Uh, One of the most prevalent explainable AI strategies overlays heat maps on input data to communicate the relevance of individual parts of the input on the prediction. Layer-wise relevance propagation is one of those heat map strategies. But what makes layer-wise relevance propagation particularly important, and what are the desired properties of heat map explanation methods? Hello, everyone, and thanks for joining us. My name is El-Sharif, and I'm a steering committee member at Aggregate Intellect. Today, we are very pleased to be hosting Anna Saranti. Anna is a doctoral student at the Technical University of Graz, working with a group of Professor Andres Holzinger. Anna completed her master's in computer science with distinction with a thesis on applying probabilistic graphical models and deep reinforcement learning in learning-aware applications. Anna is currently employed in the project, a reference model of explainable artificial intelligence for the medical domain, and she has worked as a tutor for machine learning at both TU Graz and TU Vienna. Anna has experience as a software developer and data scientist in several industrial companies in Austria. Anna will be presenting Explainable AI with layer-wise relevance propagation. To the audience, please post your questions in the chat, and we will be asking your questions immediately after the presentation. So without further ado, I will now turn the presentation over to Anna. Please take it away.
Hi everyone, I'm Anna, and today I will start presenting one of the heat mapping methods that are invented at the Technical University of Berlin that we use in the Medical University of Graz as well as the Technical University of Graz to explain neural network models. I'm thanking Ali for inviting me for this talk, as well as my supervisor and mentor, Professor Andreas Holzinger. The outline of my presentation will be as follows. First, I will make a brief introduction about heat maps and how do they look like so that we have a vague idea what heat mapping methods are and what are the benefits. Then the points 2, 3, and 4 refer to some motivational examples comparing the layer-wise relevance propagation that from now on I will only call LRP abbreviated, versus sensitivity analysis, which is one of the other heat mapping methods that already exist. There are plenty of others too. I will proceed to show how LRP is beneficial for whole dataset analysis. We deal with big data. Heat maps usually present us stuff that are particular to a particular input. So it's very important that we have heat mapping methods that help us with big data, and then we can see how they also we can be helped with LRP with perturbation analysis, changing our data set accordingly to improve the performances of our models. Points 5, 6, and 7 are the second part of my talk and deal mostly with the basic mathematical principles behind LRP. I will also present one numerical LRP task that one can solve on paper. And I will also talk in the end about what are the main key benefits of LRP so that one has takeaways, so to speak, for fully connected neural networks, convolutional neural networks, LSTM, and newly now for graph neural networks. Of course, the literature will be also given, and in the end, I will answer potential questions. So what are heat maps? This is one image from an application of LRP in a medical classification. Let's think of a simple binary classification task where a neural network is confronted with images of tissue that can be cancerous or healthy. And this cancerous images, these tissue images, usually are whole slide images that we also have in the Medical University of Graz. They have very big size, and one can zoom in also to see details. And what we know from doctors is that parts of images that are very good structured most of the time have very good form and are sometimes like agreed, and they're not dissolved. When we see, for example, on the right down part of the input image, that we can recognize the individual cells, they are near to each other, they are not dissolved, then this part, isn't considered cancerous. But the upper left part, which is the biggest part of the image, we cannot recognize the limits between cells from each other. And those deformations, this non-structured cells that one gets into another, they are the first indications of cancer. Very, very simply put. So ideally, what we would like is that when a neural network is trained on that kind of images, that it can recognize that the biggest part of the image indicates that the patient has cancer, and correspondingly tell us that what contributed the most in the input image for this decision is this part, the left upper part of the image, where we have those deformations. The part of the image that looks a little bit healthier and more organized, this is something that goes against the prediction of saying that this patient has a cancer. And usually, doctors, as well as neural networks, have to see a lot of images of cancerous tissue to decide if a patient has cancer or doesn't have cancer, or in what stage the cancer is. So the question is, what is a good heat map? How do we know that a heat map is informative? How do we know that a heat map is more interpretable? Now, we can go and say that the sensitivity of an input pixel is the norm over all partial derivatives. Let's assume that we have a neural network that we all know computes a linear function f of x. We could compute this value and could print it out and say that sensitivity analysis tell us how much a small change in the pixel p affects the prediction output of our neural network. The direction of the change is lost because of the norm, but let's not concentrate on that for now. Of course, the requirement is that we have locally differentiable neurons. But what actually happens? This is one of fictional examples of what can happen in a classification example. We have the blue dots and the green dots in both cases. On the left side, we see what happens with sensitivity analysis, and on the right side, we see what happens and what is computed by LRP. The binary classification task differentiates between the blue ones and the green ones and has already classified them. And in the dashed line, we see the decision boundary in both of the cases. Now, the decision boundary on the surface plot has here one of the examples where it belongs to the green class. And here we can take one particular point of the blue class. Now, what do we see? We see that the gradient of the function at the prediction point does not point to the nearest point of the other class. It just points to a local minimum that, if we imagine this surface plot to be expanded in a consistent way, it shows to a direction, to a local optimum that it's a little bit too far. The closest point is at a completely different angle, right? So let me repeat that. With black, we denote local gradients, and with red, we see the approximation of the function that is computed by the neural network by Taylor expansion that is used from LRP. So this is a depiction of comparing on the left what SA does, which is finds out what places in the image would make it belonging to another class when we change something in that area around the pixel, whereas in LRP, the argument is that we show what is really, really relevant for a classification. So let's see the result of the heat maps in those two cases. We have an input image and we have also a classification. We see how scattered the sensitivity analysis heat maps look like and how the LRP heat maps look like. The LRP heat maps look a little bit more concentrated on particular characteristics of the input image that played a higher role to a particular prediction. And there's also one differentiation between sensitivity analysis and other heat mapping methods with LRP, which is the areas that are denoted by blue. This shows that there are also parts in the input images that have negative, so-called negative relevance, meaning that they speak against the prediction. And I will come to this a little bit later. Again, I would like to show also one very representative example from the TU Berlin group, which shows what's the difference between a sensitivity analysis heat map, which again is scattered. Yes, we see that in the middle of the image, there is importance, but we cannot consider exactly what are the characteristics of this bird that contributed the most. Now, the edges of the bird and the change in its color and its feet and the place that it sits on are much more relevant than this middle area that could be anything. So this is a very fundamental difference between other heat mapping methods and LRP from the visual aspect or from the interpretation aspect. Now, we can imagine that one data scientist involved in a very big project doesn't have probably the time to, after training a neural network with a very big data set of images, sits down and systematically goes through all the heat maps and looks at where is it red, where is it blue, to find out all the explanations. So how can we be helped by the heat maps, although we have very large data to deal with? What the researchers of the Technical University of Berlin found out for the Pascal-Vogt 2007 dataset was that almost 1/5 of the horse images had a tag on the left down side. And they found out that a high-performing neural network that also won a prize that did classify between all those different classes of those images, containing horses, containing cars, buildings, and so on and so forth, was basing its good performance in cases where it saw the horse based on this tag. So what they actually did is that they put a tag in images that contain the card, and boom, the neural network said, this is a horse, which actually showed that neural networks base their decisions on correlations, and that layer-wise relevance propagation can detect those so-called clever hands predictions, or cheating, as we might say. What we also see is that humans have a preconceived notion about what a neural network should do and how a neural network should base its decision. So it needs a human needs a good explanation about why the neural network does something and why does a neural network decide something. And if the decision is not overlapping with what a human expects, then it's time to take action. And they decided to invent a method where one doesn't have to look all the images. One only has to take the heat maps of a particular class, compute the eigenvalue spectrum. They used also TSNA. And if one sees relatively large gaps, one can assume that the neural network did take a different strategy at each time to classify an image as containing a horse. It can be that a horse exists in the image, or it might be that there's a tag in that image, or it can be that there's a particular background with grass and a nice park that's always occurs in the images of the horse. There were also different experiments with data sets containing images. And there's also one example that this group presented where one set of the images were taken by a particular photograph by a particular machine. They all were of the same class, and they had an artifact on the surrounding of the image, which was representative of this photograph. And this is why the neural network did decide on that particular class all the time, which was actually wrong. So LRP provides us also actionable insights, not only to change the model and check what's wrong in the model, but also change what's wrong or potentially wrong in our dataset. And let's now jump into how LRP can be used on LSTMs. LSTMs process sentences, process sequential data, and we can also use it, for example, in an LSTM that does a sentiment classification task. Takes as an input a data set that has movie reviews, has usually criticism, and has 5 classes from very negative to very positive. And here in this image and in this slide, I'm comparing sensitivity analysis results and LRP results. LRP results have negative relevance against the very negative class. So all those sentences are classified by the neural network as containing very negative criticism about particular movies, and LRP has negative relevance to that. It picks up that, for example, funny is something that's actually considered positive as a criticism. Something that's called suspenseful or originality is something that's actually positive. Nevertheless, those sentences have enough bad words in them, like neither, nor, or horrible, that were enough for the neural network to decide correctly and say, this is actually a negative criticism. But if we compare, for example, sentence 10, and we see that here there's this originality, we see that sensitivity analysis picks up that originality is important for its decision, but it doesn't tell us if it had a negative or positive sentiment in it. Here, by LRP tells us, okay, this is actually a positive word, but I have this neither inside. I have lost inside. And those two are stronger than originality. One of my favorite examples is, for example, sentence 6, where the master of disaster is there. Here, sensitivity analysis tell us that for a particular reason, master is important for its decision. But LRP says disaster, it's much more important, and master can be also thought as something that's positive. Nevertheless, it picks it up right, it classifies it right, and Drake is also something that has a very negative, is negative criticism about this movie. And perturbation analysis is something that's very easy to do in LSTMs. It's also something that is used in state-of-the-art convolutional networks, where one calls it their region perturbation. Let's see it in the LSTMs. The thought is, okay, I did my analysis with LRP. I did it also with sensitivity analysis. I can also pick up random words and delete them. What if I delete one of the most important words for a particular prediction? What if I remove this Drek? What if I remove from, let's see, here, this horrible? What will happen? Because for each sentence, I can sort the words according to the relevance. And for each method that I'm using to explain what's relevant and what is less relevant, what's positively relevant, what's negatively relevant, and what's probably around neutral, being neutral, I can sort all those words. And I can say, if I remove that very negative word, will the classifier predict the same class? And what the researchers showed is that, and what we can see on the left side, is that when the classification is correct with a target value, sorting words and removing words by decreasing relevance, then we see that the performance drop is very high and very monotonous when we apply LRP, whereas for sentiment analysis, it isn't that fast. And on the opposite side, if we have a misclassification, if we remove first the words with the greatest relevance, then the second word with the second most high relevance, then the misclassification performance increases. So this is also a way to validate that our neural networks and our explanation works properly. And now, since I'm mostly finished with the motivational part and the application part, I will dig into a bit more mathematical basis about LRP. This is part of, let's say, something that I would recommend to students to get their hands dirty and be a bit more hands-on with LRP. I will repeat now what a fully connected neural network is. It's a network that it's divided in layers. We have the input layer and an output layer and a number of hidden layers. Each layer contains a number of neurons, and all neurons from one layer are connected with the neurons of the next layer, with all neurons of the next layer. In the early days of AI, an input image is processed by a neural network. For example, for a classification task in this way, we don't have for now, convolutional networks with skip connections for this part. The neural network just computes a nonlinear function f of x. And let's assume that for our example purposes, the function that is computed ideally, or what we want the neural network to compute, is to output a 0 when there's not a particular object in the image, or having a higher than 0 value when an object is in an image with some kind of degree of certainty. Let's make a concrete example. Let's assume that we have a data set that we wanted to classify images not containing a building and others that do contain a building. So simple as that. The result of LRP when applied, for example, in a simple convolutional neural network can be as follows. It would decompose the decision of the neural network into contributions of individual input pixels, and would also highlight to what extent the pixel P contributes to explaining the classification decision of the network f of x. One can also imagine that one would get heat maps for correctly classified and misclassified. I referred to that in the example with the LSTM some minutes ago, but let's see this with a particular example. Let's assume that we have a neural network that classifies the MNEST digits. We have a 10-digit classification from 0 to 9. They're all handwritten. And we see that, for example, all inputs of the upper row should be classified as class 0. This is what were given to us as labels from our users. The second one would be 1, the third one would be 2, and so on and so forth. So the heat map of a correctly classified 0 as 0 shows that those parts of the image, for example, this part that's empty in the middle, was one of the most important things for classifying this 0 as 0. The heat map of A does not make so much sense. And this is something that it's very problematic for heat maps of misclassified inputs, regardless of what input it is. It can be an image, it can be text, it can be a graph. But heat maps of misclassified inputs doesn't make most of the time sense. But nevertheless, for correctly classified examples, what do we see in the heat maps, or what we expect to see in the heat maps for a good trained network and a correctly working network according to our preconceived notions, is what differentiates, what discriminates input samples from each other. So if we could think of a neural network that's only trained to recognize images of zeros and images of 8, one can expect that those curves that appear into the 8-digit will be the ones that differentiate it most from the 0-digit that has this hole in the middle. And we expect that the neural network is concentrated on those differences to classify those 2 digits correctly, right? Okay, now, one more thing that's very important to repeat is that the neural network training procedure is feed-forward, but the network is trained by backpropagation of the error of its prediction with the training data. LRP applies relevance backpropagation, but I would like to really put emphasis on the fact that this backward pass is happening once in an already trained neural network. Please don't mix up the backward pass of the relevance propagation that happens after the training with the backpropagation of the error that can happen a lot of times until the neural network performance converges. Okay? There's only one exception, which is the graph neural networks case, which uses multiple backpropagation passes. This is something that's currently in development by the Technical University of Berlin. We will not go and we will not see this, but this is the only exception where multiple backpropagation passes exist. We will deal only with relevance backpropagation that happens once after the training. So we assume, again, that we do have a fully connected neural network, input, some hidden layers, and one output. Here, it's trained. We can pass then a new input in our test set. We can compute the output, and from the output, we let the relevance flow or go back or being backpropagated from the upper layers to the lower layers. Usually, the input layers is depicted by E or I in English, and J is usually one of the layers that's coming after the I layer for notation reasons. And again, with a concrete example where the input is going to be a cat and the neural network is trained, we do a forward pass where our input is put into the network, and then after the network is trained and after the input has passed on to the output, then the relevance propagation is computed from the output to the input, and the resulting heat map, we expect it to be one where the importance is concentrated on the head or on the torso of the cat, and the background hopefully didn't play a very important role in the classification that this image contains a cat. LRP is based on something that we learn in the university. This is Taylor expansion. Let's repeat that. Taylor expansion of a particular function f of x at 1 point a is expressed by the following equation. And by the same means, one can write the f of x as the relevance in one of the layers, let's call it G, that comes after the layer I. And ideally, if we think that all those terms after the second one, the one that uses the second derivative, actually, can be somehow minimized or ignored for now and put into a variable called epsilon. And ideally, if fa is also 0, then we can decompose the relevance of one layer according to the relevance of derivatives and the x of I minus the root point, so to speak. This is why we have this tilde here. So if we could find some root point where the function of A was 0, then we could decompose the relevance of one layer to the inputs of its previous layer. Now the point is how to find this A. So we do want, if we do a Taylor expansion, that this A is near enough to X. Remember before that I said talked about when I showed the image for sensitivity analysis, that I showed this area between one class and the other one. So it's very important that we find the nearest point that's classified as the other class. And here is one of the fictive examples that the group of TU Berlin showed of how to find this root point. Of course, this is an optimization method issue, but to explain it in a best way for students, they use this cartoon image, as they say. They assume that we have a neural network that is trained, as I said before, recognizing images containing a building and ones that not exactly don't contain the building, but they're blurred. So the blurred images containing buildings are the ones that have the label as not containing the building. One could also think an example where this neural network was trained in such a way that if the basics of the building were actually deleted, then that would be also one valid root point. That would be also a near enough image to this input where which we are searching the root point. So this is an input that's classified as having the building. This is the nearest image to that is classified as belonging to the other class. We compute the gradient. We compute also the difference between the input and the root point, and the outer product of those two creates us the heat map. So the goal is to, after we have found the root point, we redistribute the neural network output onto the input variables and the relevance of each layer J to the lower level relevances R of I. How to find the neighboring point, as I said before, it's an optimization method. Lots of methods are used, like line search and so on and so forth. A good root point is one that removes elements from the data point that cause f of x to be positive, cause f of x, for example, to detect the object. And usually one can see in the papers that there's a similar image, but the object is not recognizable from the classifier. Hence, the output is 0. It's the other class. What are the properties of LRP that also make it different than other heat mapping methods? The conservation property is one of the most important. There are others that can be found in the literature that I will present in the end. The conservation property states that the sum of the relevances of each layer are conserved through all the layers. And this is also very useful when one goes and computes the relevance layer by layer. It's useful when one wants to write unit tests, when one wants to do quality management, to check that the numbers that one has computed by a program or at hand, that they are correct. And I'm also presenting here the rectified linear unit, which is one of the nonlinearities that one can use for the task that I will describe right now. This is one of the simple examples that can be used for learning LRP by hand and numerically. This is one of the smallest neural networks that one can imagine. It has 3 neurons in the input layer, 5 neurons in the hidden layer, and just 1 neuron in the output layer. It uses the ReLU nonlinearity in the hidden layer. The connections are not presented here for abbreviation reasons, but they exist. All of them exist. And the mathematical equation of x of j, because we have the ReLU nonlinearity, is the maximum of 0, or the linear sum of the inputs here and the learned weights plus the bias. And the output x of k is the sum pooled of the inputs of the hidden layer. And the relevance of the output layer is the sum of all inputs that it gets. The relevance of the hidden layer can be easily computed by Taylor decomposition on the root point 0, because since we have the ReLU, everything that passes through is either 0 or something positive. So the root point is actually the one where all inputs are 0. And the relevance of the jth layer is computed by this equation. And to compute the relevances of the input layer, the extended solution, one of the potential extended solutions, is one where the relevance is weighted proportionally by the weights connecting the one neuron of the input layer and one neuron of the hidden layer. And there are a lot of ways how to go backwards and find the relevances of even previous layers and much more difficult activation functions, and they can be found in the relevant papers. Here is one of the simplest examples, and I can also show here one example to see that LRP produces different kinds of heat maps, and it's not only producing negative to positive from blue to red, but also can produce much sharper heat maps to much denser image heat maps. Here, I've found this example very important because this is a classification that takes this image, but cannot actually say if it's a dog or a cat. Actually, you do have an image that contains objects from both classes, right? So we expect the neural network to be quite irritated. So with different rules of how to backpropagate relevance that do obey the conservation property, one can see that for this neuron, this input be recognizing that this image is classified as a tiger cat, it shows that the positive relevance is on the cat, and something that doesn't help the neural network to say that this is a cat is here with the blue. But if this neural network predicts that this is a dog, then the dog played the most positive role for the prediction, and actually the cat is something that irritates the network towards to not predicting with such a great performance, with such a great of certainty that this was actually a dog. And those LRP variations can also change the how dense the heat maps will be and how detailed the relevances will appear to the user. There are also cases that for small weights, there are also small variables like class epsilon, which is adjusted so that one doesn't lose relevance and things appear in the heat map and not get lost in cases that we have very, very small weights. So the LRP task that one can do also on paper uses the equations above to just compute numerically the relevance of all layers of the network depicted in the figure. And I suggest most of the time to students to use own weight values and own inputs to see how this juxtaposition and the combination of inputs and weights, how do they produce particular outputs, particular fictive classifications, and how the relevances are backpropagated. They can also think of using weighting schemes that are typically used in neural networks. Usually what happens is that they pick up inputs that are very high and positive value, weights that are also high that contribute to a particular output. But sometimes they see that if they have a very strong input, and they use some very negative weights, then something in between comes out. It's always very interesting, but that's actually what it's necessary for learning how those two play together for a particular output and what inhibitory neurons are. And it's also very important that they can also use those conservation and positivity rules and other properties of LRP to check that all the things that they have computed on paper or they will program at some time point, that those are correct, right? And of course, providing description of the interpretations in written form is also very important. The code for LRP is on the GitHub repository of the TU Berlin. It's called Investigate with Neural Network, and there's also one more which is called heatmapping.org, which shows more presentations and more applications for medical applications and other industrial tasks. So to close up and to also give to the audience takeaways, what are the benefits of LRP? First, more interpretable, more concentrated, not scattered heat maps. We have positive and negative relevance. We don't just have low relevance and high relevance. We can discover artifacts in big data set in a semi-automated way. We do have actionable insights. We know what we should change in our model, what we should change in our data set. And the third one is we have principles applied to new neural network architectures that are now coming to be state-of-art, like graph neural networks. And it also supports quality management by all those checks, principles, and properties. The literature consists first of the main LRP paper. If somebody wants to learn the basic mathematics behind LRP, this is the paper that I recommend from Grégoire Montavon. The differences between sensitivity analysis and many, many images, as well as math, are in those two papers. There are other papers that compare LRP with other explainable AI methods that produce heat maps. And the whole dataset analysis is in this paper from Sebastian Lapushkin. For LSTMs, there's a paper from Aras Leila, and there's also an upcoming paper from Thomas Schnacke about how to apply LRP in graph neural networks, which is ongoing work. And that was that. Thank you very much for listening, and I'm happy to hear your questions.
Thank you, Anna. We will start the Q&A part of the session, and we will be presenting Anna with live questions as well as questions we've received in advance. The first question here I have from Nikre is maybe a very broad question, but do you think explainability methods can be used as feedback to improve generalization?
To prove generalization?
Improve. So, yeah.
They can be, but what I think it's even more, as far as I know, is that to test and exercise, if I might put it that way, generalization, there are a lot of data sets that are created artificially to do that. One of the first ones was so-called Clever, which is expanded to Clojure, Cleverer. There's also one that's called Curie, Bongard Logo, the one that we created in the Institute, which is called Kandinsky patterns. Those data sets are defined and created by means of when they're used as an input data set for neural networks to exercise their generalization capabilities. So I would suggest more those methods first. Now, explainability could be applied after that to show what the neural network has learned, if one has generalization or not. But the first thing to do to check generalization is to actually use those data sets and see that a neural network trained on that kind of data sets, the training set of those data sets, has a completely different performance from its validation set or test set. And that is the first step, and that is most of the time enough. Explainable AI can be an add-on to that.
Okay, excellent. Thank you, Anna. Appreciate the answer. Now, maybe I'll ask this broad question as well. So, is LRP considered a post hoc method? I'll just leave it at that. So,
well, I would in general say yes, but it has also, how can I say this? It has also some constraints that I briefly referred to. It has also some requirements. It's not something that's so easily applicable to a neural network that has skip connections And I saw, for example, the paper of Thomas Schnacke, and I saw that, for example, LRP works completely different in a graph neural network. So it depends also on which architecture we're talking about. But I would say post hoc.
Okay, so yeah,
Mostly.
so it's post hoc methods that's specific to maybe neural networks. And are there specific classes of neural networks where LRP is applicable and specific classes where it's not? Or is it something that could be applied to any neural networks?
I would never say any, because
Yeah, okay.
I wouldn't say any. I wouldn't say any. The group is very careful about the constraints of LRP, and they are very open about it and very, very detailed about it. They have the requirements about which activation function sometimes they have applied their method to. They are very open about which architectures they have applied and provide to us free. So I can remember reading papers where they told that activation functions have to have particular properties. That, for example, skipped connections. I haven't seen papers with examples of convolutional networks with skipped connections. I don't remember seeing that. I hope I'm not unfair, but it's easy to see this, because this relevance propagation does a flow from the output to the input. And also, I remember vividly that the LSTM paper from Leila has also some constraints on the LSTM. So we cannot say all of them, but we can say that most of them, and each time a new architecture comes out, they try to find how LRP can be adjusted to this architecture, although they will write in the paper what constraints do they actually have.
Okay, beautiful. So it's a post hoc method for explainable neural networks that comply with certain constraints that vary from one neural network to another. Would that be a summary? Okay, beautiful. Now, another question that I received here as well: if LRP makes a neural network explainable, how do you define explainability, and when do you know what explainability has been achieved? So if we're saying LRP makes neural networks more explainable, what is the definition of explainability, and how do you know that we have an explanation that's working? I mean, again, very broad, but it's more of an opinion than a concrete answer. Yeah.
A little bit of that I also presented very carefully in the lecture and in the presentation. It's debatable what an explanation is, because there's always a reference to a human. At least for my professor and mentor, Professor Hollensinger, he is one of the persons that promotes the human in the loop.
Yes.
Who decides if an explanation is good is the human, and many times, at least in the Medical University of Graz, we have already, as I told before, preconceived notions about what a good explanation is. Of course, we know when we don't like an explanation. As I showed the example with the tag and the horse, we don't want a neural network to base its decision on the tag. We call it cheating. It doesn't overlap with our expectations. And if, for example, a neural network bases a decision of if something is cancerous against something that's healthy, and it doesn't overlap with the human, then our first indication is to see what was wrong, what's happening. It's not that we call this explanation bad per se. I would say it's just an alarm to check what might have been wrong. And it can be many things, and it can be our data set, and it can be the code, it can be the human itself, it can be a new insight that the neural network has grasped and the doctor didn't grasp. Hopefully not, but it can happen. So there are many reasons why a good explanation might not be good, or a bad explanation might not be bad. An explanation is for me something that tells us how the neural network took its decision. It can be good, it can be bad.
Okay, and that's as specific as we can get. This is a very, the answer is it really depends. So, okay, maybe I'll go back to just maybe pointing out or the confirming the mechanisms in which LRP works. Now, LRP is providing pixel level explanations. Does it have a mechanism of aggregating those pixels into regions like superpixels, like other methods do?
One of those that's called composite strategy doesn't gather this as superpixels, but somehow eliminates the parts of pixels that are just alone pixels. I would say it doesn't blur it exactly, just spreads out a little bit more visually the positive and negative relevances, and it doesn't have it pixel wise so detailed. Not so. It doesn't look like salt and pepper, blue, red. Parts, but if most of the pixels in an area have a positive relevance, then it makes them more red, so to speak. So I wouldn't call it superpixel, I would call it region of relevance.
Okay, and really, when we're talking about LRP, it's really a class of methods, and there are so many variations within LRP, depending on which neural network it's optimized for, if you will, that the answer could differ between one variation of LRP to another.
Definitely. And also, it also takes into account that different users would like different details to be presented to them. A doctor would like to zoom in into details of cells. Somebody else that looks at image classifications of horses and buildings just wants to see where the highest relevance is, and that the network didn't base its decision on the background. That's completely different purposes.
Okay. Now, broadly speaking, does LRP generate confidence level or a confidence score in the explanations? Like we've seen some other methods that might issue a fit score that we feel this explanation, or we believe this explanation is a good fit for this classifier. Is there such a concept in LRP of issuing a confidence score in what it's explaining?
Not that no, I haven't. I can't recall learning something like that or seeing something like that in the papers or in the presentations. No.
Okay. We are unfortunately getting close to the end of the hour, so I'm going to have to stop there in terms of questions. Before we wrap it up, are there any final thoughts that you would like to share with us, Anna?
No, I'm just want to thank you again for the invitation, and of course thank the TU Graz that I'm currently doing my doctorate, and my professor Andreas Holzinger as well.
Okay, and Anna, I in turn thank you for a great presentation, and thanks all of you who joined us online and submitted questions in advance. To see more free content like this, please visit our website at ai.science and log in to access the slides from this and other sessions. Also, make sure to subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. This concludes our event. Thank you for watching.